Hello, today's topic is internal forces and beams, and this is part 2. In this part, I will show you how to draw the internal force diagrams for simple beams, and how to do it quickly and efficiently without writing equations. Some professors require writing equations to draw the internal force diagrams, so you need to ensure whether these equations are necessary for you, or if you simply need to draw these diagrams and that's it. Without writing equations, the diagrams can be drawn much faster. So this is definitely a video aimed at those people for whom drawing internal force diagrams is just the beginning of the task, and not its main purpose. Okay, so let's get started. The first example. I chose this beam loaded with a concentrated force of 8 kNm and a distributed load of 10 kNm. I will try to draw the diagrams in this video using PowerPoint tools in real time. I hope it comes out fairly aesthetically pleasing. So here I marked the characteristic points A, B, C, D at the top. We must know that at the hinged support there are two reactions, a horizontal component and a vertical component, VC and HC. Looking at the beam, we see that there is no horizontal force acting on this beam, which means the horizontal component of this reaction, HC, will equal 0, as there is no force it could respond to. And here at the sliding hinged support, the reaction perpendicular to the direction of sliding is VA, which we will calculate shortly. Now we will write the static equilibrium equations, so we can either do the sum of moments about point A or the sum of moments about point C. Always consider which equation would be best to solve first. We could also do the sum of vertical forces, but in that equation there would be two unknowns, VA and VC. By doing the sum of moments, we can immediately calculate one of those reactions. I chose the sum of moments about point A, which means I consider clockwise moments as positive, so we have 8 times 2 minus VC times 4. We will also calculate the resultant of the distributed load, which acts at the center of gravity, and its value is the value of the distributed load, which is 10 times the length of the beam at which this load lies. So 10 times 4 equals 40, and this resultant acts at the center of gravity. As this is a rectangle, it is simply located in the middle. So we have 8 times 2 minus VC times 4 plus 40, and here it is 2 up to here and then 4, so together 6. Equals 0, from which I get VC equals 64 kN. Now the sum of vertical forces also equals 0, so we have VA minus 8 plus the VC, we already calculated 64. Minus 40 equals 0. From this, I get VA equals minus 16, and just like in the previous video at the end, I changed the sign to positive and the direction of the reaction VA to the opposite. So this reaction VA is always in the value of 16, but not this upward reaction that I calculated, but downwards. So this reaction VA is 16, but downwards. Okay, and now that we have the reaction, we can draw diagrams. And we can also do a check. I did a check here as the sum of moments at point B. It's good to do a check at such a point where no reaction that we calculated passes through, so that both reactions are included in the check. So we have minus 16 times 2, which is VA times 2, minus VC, so minus 64 times 2 plus 40 times 4 equals 0. The left equals the right, that's correct. And now we can draw the diagrams. So I prepared an area for drawing diagrams. Well, most often it is done like this, simply under the beam, but I have it a bit differently here. Now we have a few rules. If there is a shear force applied on the beam, it may also be a reaction, then on the shear force diagram we have a jump equal to the value of that reaction. If a moment is applied to the beam, then on the moment diagram we have a jump equal to the value of that moment. And we need to know this. I will also draw this 40 from the continuous load here, well, like this. First, at the beginning of the beam, we have a jump equal to the reaction VA. This VA turned out to be directed downwards, and its value is 16. So first we have a jump of 16 in the direction indicated by the sign of this reaction. Then, on this part of the beam, there is no shear force applied, so the value does not change. And this is a negative value, 16. Next, we have an applied 8. It is also directed downwards, so we now have a jump of 8 downwards. From that 16, we go to the value of 24. So here's 24. And on this segment BC, there is also no shear force, so the value does not change. This is also a negative value. Now we have a support here, where we have a reaction VC equal to 64. So on the shear force diagram, we have a jump of 64 in the direction indicated by the arrow, which is upwards. So from minus 24, we add 64, which brings us to 40 positive. Here is positive 40, and now when a continuous load appears, the shear force value changes linearly. And from the initial value, it always decreases by the value of the resultant, that is, by 40 linearly. From there, we drop linearly by the value of the resultant continuous load, that is, by 40, so from 40 down to 0. Here there was a positive value. This is what the shear force diagram looks like. And we can already draw one valuable piece of information from this shear force diagram. If under a continuous load on the shear force diagram the graph changes, sign here, then we would have an extremum on the moment diagram. And since under a continuous load on the shear force diagram the graph did not cross to the other side, did not change sign, there will be no extremum here. So a little less counting. Okay, now a moment. The moment is a bit more complicated. We can calculate it in two ways. First, I'll show you a method where we calculate the moment at a specific point. Then I will show you a method where we can draw the moment diagram by calculating the areas of the shear force diagram. Okay, but first the moment at a point. So we need to know that, as I mentioned earlier, if there is a moment applied to the beam, or it is present as a reaction in a fully fixed support, then on the moment diagram there is a jump equal to the value of that moment. And if there's no external moment applied, then there's no jump. So the conclusion is that the moment at the ends of the beam, since there is no moment applied here, must be 0. So from both sides, if we want to calculate, we start from the value 0. And then if we calculate the moment at point B, which is here, we only consider the 16 that is on the beam. It turns counterclockwise. So looking from the left side, it's negative, which gives us minus 16 times 2. So the moment at this point is minus 32. We have positive values for moments at the bottom, so the negative is at the top, and it is minus 32. And one more important rule, on the moment diagram we have 1 degree of equation higher. So if there is a constant value here, then we have a linear function here. If there is a linear function here, then we have a quadratic function here, which is a parabola. Also, with trapezoidal loads, it may happen that on the shear force diagram we have a second-degree parabola, that is quadratic. Then on the moment diagram we have a third-degree parabola. Okay, so here the value was 16 times 2, which is 32. The numbers were a bit awkward, but unfortunately. And we connect them linearly. And here is the negative value. Okay, then we can calculate the moment at this point. We can also calculate from the right side if it's easier for us. And it is arbitrary whether from the right or left side we should get the same result. So let's calculate this time from the right side. From the right side, when we calculate, we must remember that when we cut the beam from the right side, these are positive normal forces. These are positive shear forces, which means they have this direction, and positive moments have this direction. So this 40, which will turn clockwise at point C, it will turn negatively. So the moment at point C, looking from the right side, is 40 times the arm 2, which gives us 40 times 2 equals 80, and is negative 80, so upwards. Negative 80. And from that 0 to this 80, we connect with a parabola. 80, and it is a negative value. Now let's calculate from the left side. From the left side, if we were calculating at this point C, then we have it like this. Minus 16 times 4, that is minus 64 minus 8 times 2. So minus 64 and another minus 16, which is minus 80, that's correct. How do we connect this 32 with this 80? Since there is a constant value here, we connect it linearly. Well, I'll tell you, I thought it would look worse. It definitely doesn't look beautiful, but I think you can see something. Of course, the slope of this linear graph changes here. There is a kind of bend, just like that 8, you could say this graph bends here at the moments. And this is what the moment graph and the shear force graph look like without writing the functions. Of course, with commentary it took a bit longer. But in reality, this graph could have been drawn in 3 minutes. So the method is nice. I will show you on this example how to calculate it using the areas of these shear force graphs. We could calculate the area, first the area of this rectangle. And that area equals 16 times 2, which is height times length, so 32. Once we calculate all the figures, you will see that this is also a nice method. 24 times 2 is 48. 48 is the area of this rectangle. And then there is this triangle, which is 1/2 times 40 times 4, which is 2 times 40, so 80. Now, if we move from the left side, the sign of this graph causes that, which means in this direction, the moment graph changes, according to the sign of this shear force graph, so moving from the left side. And if we move from the right side, it is the opposite. So the sign of this graph causes the opposite change in the value of the parabola, meaning the parabola or another graph depending on what shape we have. So yes, knowing that we start from 0 and have to move 32 in the negative direction. So we end at 32 and we know we connect it linearly because there is a constant value here. Then we are at this 32 and we have to move 48 again linearly. And in the same direction, so also in the negative direction. So that was minus and here's minus, which means they are adding together. So 32 and another 48 when we add it, it is indeed 80. And we move to that 80. And then we are at this 80, and again, looking from the left side, we have to move towards plus. We have to move towards plus by 80, and we are supposed to move with a parabola. So, since here it is linear, we should have a parabola here accordingly. We connect this graph with a parabola from 80 to 0. I actually prefer to calculate areas rather than moments at points, because when there is a longer beam, it is easier to look at the graphs and look at their areas rather than calculating the moment for each point. I think it's easier. But what you prefer, you'll choose for yourselves. So thank you for your attention. I hope I helped. If you have any questions or comments, feel free to ask and leave comments under the video.